Josh Paul back here with O-Chem Simplified, and today we're going to be going over the acid bases, and we're going to be tackling some questions that are going to test our knowledge on whether or not we understand how to determine which proton is going to be deprotonated during certain types of acid-base reactions. So without further ado, let's just go ahead and dive right into the first initial questions. So as we can see here, we have a ranking question, right? In which case we're going to be ranking in terms of increasing acidity. So the biggest thing that we have to do right off the bat is just figure out what the pKa's for the actual molecules that we see, right? Once we know the pKa's, we can determine whether or not one molecule will be more acidic, or I should say whether or not the proton from that molecule will be more acidic when compared to another molecule. So let's go ahead and see what the pKa's for those values are. So as you can see now, we have the values for the pKa's for each of the protons coming from the molecular species in front of us. So as we know, the lower the pKa, the stronger the acid. So whatever has the lowest pKa should be corresponded to the lower values in terms of our ranking. So our strongest acids are going to be 1, 2, 3, and 4 in that increase in order. So right off the bat, you should see that the HBr is going to be the most acidic because it has a pKa of -8. The hydronium molecule is going to be the second most acidic because it has a pKa value of -1.7, and then the primary alcohol, and then your cyclohexane. So we're going to go ahead and show you what that looks like. So as you can see here, just by memorizing the pKa's, we were able to list out all of the pKa's for each of these molecules, and then immediately go straight into ranking them without having to do any extra work or with Aereo and figuring out whether or not this atom should be compared to this atom and whether or not there's any resonance or the effect of induction, right? By simply knowing the pKa's and us having the technology to simply just Google search or memorize the pKa's, we simplify the amount of work that we had to do, in which case now all we had to do is just compare which one has a lower pKa value. So here we have another problem, very similar to the one that we just did. Same thing, we have different molecular species and different hydrogens or different protons on those molecular species that can be taken away, right? And now we're comparing between these molecules which of these protons is going to be more acidic. So let's go ahead and do the same thing and right off the bat list out the pKa's for each species, for each proton in the molecular species. Right? Because we know once we know the pKa, we can determine the ranking for acidity. Now that we have the pKa's listed down, we can now rank them because we know the lower the pKa, the stronger the acid. So we see H2SO4 is going to have the lowest pKa, and then followed up by the carboxylic acid connected to the benzene ring, then followed up by the ammonium ion, then followed up by the thiol, and then the primary alcohol. Right? So we know these pKa's because we've already memorized them. So now all we had to do is just simply list them down and then rank them in order of lowest to highest in terms of the pKa values, which is going to correspond to the lowest pKa's being the strongest acids, right? So here's just one more example of how you can see why knowing the pKa's makes your life a lot easier, because now you don't really have to worry about anything conceptual. You can just simply list down the pKa's and go straight to ranking. So go ahead, pause this video or let it play out a little bit and see if you can understand, this example that I just did with the ranking of the pKa's. So obviously, your alcohol, right? So you see that you have a phenol, right? Phenols, I don't know if I mentioned this in the other video, but phenols have a pK of 10, right? And primary alcohols obviously have a pK of 16. Your alkynes will have a pK of 26, And here's something to note, right? Remember, in the problem sets, we're going to be going over different examples and different tips that I've learned from going over organic chemistry. And here's a little tip that will help you, right? Primary alcohols will be more acidic than secondary, which will be more acidic than tertiary alcohols, right? So if you know right off the bat that you're dealing with a primary alcohol versus a tertiary alcohol, right? Even though they're both alcohols and will relatively have pKa's around 16 to 18, we know that the primary alcohols will be more acidic, meaning they will have a lower pKa value. So here's an example of something you might see on a test, right? So in the previous examples, all we've been doing is just ranking the acidity of the protons, right? And what that has been doing has been prepping us to tackle a problem like this, where in a molecule, you might have multiple protons, right? That can be deprotonated, right? You can have multiple protons that can be donated, in which case you'll have an acid, right? Because an acid is a proton donor, right? So here, clearly in the red circles, we see that we have a variety of hydrogens that we can take with our base sodium hydroxide, right? In the green, you can clearly see Na plus and then OH minus. Remember, the definition of a base is anything that has a negative charge, because negative charges will be attracted to protons, which are positively charged, right? So right off the bat, let's go ahead and do the same thing we did in the previous examples. We know the pKa's for each of these specific species for the functional groups within the molecule. So let's just go ahead and list those pKa's for each of those hydrogens. And then whichever one has the lowest pKa is the one we're going to take. All right, so now that we've listed out the pKa's, we can clearly see that the alcohol is going to have the lowest pKa of around 16, right? What that means is that that hydrogen is going to be donated to the OH minus, right? So when we're donating that proton, right, well, essentially what you're going to be showing in the next slide is that we're going to see that the arrow is coming from the OH minus, attacking the hydrogen, and then whenever you're making that bond, you have to break the bond. So let's go ahead and show what that looks like. So here we can clearly see what's going on within this molecule, right? We know that the alcohol is going to have the most acidic proton, so we're going to form a bond between our OH and our H, right? That arrow from the green OH going down to the H and the bigger complex, more complex molecule. And then that bond between the oxygen and the hydrogen within our initial starting material is going to get broken, right? Because in order to make a bond between our base, our sodium hydroxide, and our alcohol, we need to break a bond, right? So it's essentially the same thing that's happening. And then, and as you can see, the product of the reaction, I just drew R just to symbolize the entire molecule, just because I didn't feel like drawing it all over again. So that's another cheeky little tip that you can use to simplify the amount of work that you have to do. But essentially, remember that there are two electrons within this bond between the O and the H that's getting broken from your starting material, right? One of those electrons, I don't know if I said electrons, but I meant to say there are two electrons within that bond. So one of those electrons are coming from your oxygen and another electron is coming from your hydrogen, right? So when that bond is breaking and both of those electrons are going onto the oxygen, the double hooked arrow indicates the flow of two electrons, right? So that double hooked arrow shows two electrons are flowing, which means that oxygen is gaining an electron. When you gain an electron, you become negatively charged, which is why you see that negative charge on the oxygen in the final product. Finally, we have another example kind of similar to the one that we just did. So with the same thing, we see that there are multiple protons that can be deprotonated. So how do we figure out which of these protons are going to be taken away by our base, our sodium hydroxide? We have to look at our pKa values. And since we know our pKa values, we can just go ahead and list them right off the bat. Now, remember that thiols are going to be less, or I should say, thiols are going to be more acidic than alcohols and phenols, conversely, right? Therefore, we know that if the pKa of a phenol is 10, the pKa of a thiol, even though we don't have that fully memorized, the pKa of a thiol in a benzene ring should be lower than that of the phenol because of the relationship we know between primary thiols and primary alcohols. Remember from the pKa chart that your primary alcohols are going to have higher pKa values than your primary thiols. And that's just a property that you have to remember. So you would know from this information that the SH is going to be the species that's donating the proton. So let's go ahead and show what that looks like. So similarly to the previous example, all we're going to be doing is simply removing the H and replacing it with the minus sign, essentially, right? Because we know that the OH minus from the sodium hydroxide is going to attack or form a bond with the H from the thiol, the SH, and then in order to make that bond between the sodium hydroxide and the proton, the bond between the sulfur and the proton has to be broken, in which case sulfur will then gain an extra electron. So I hope this video helped you understand the practical use of acid bases and how memorizing pKa's can simplify the amount of work you have to do. Please, as always, like, subscribe, and hit that notification bell, and tell all your friends, those taking organic chemistry or planning to take organic chemistry, to follow these videos, support us on social media, and allow us to help you advance your academic success in organic chemistry.